This is 2.1.1 constituents of the atom. So we start by recalling what we learned about atoms in GCSEs, that atoms are made of protons, neutrons, and electrons. The protons and neutrons are within a nucleus in the center of the atom, and the electrons orbit that nucleus at discrete energy levels. So we're going to sketch an example of what that looks like. So we'll draw an arbitrary nucleus. We will shade in some of those particles to visually show that some of them are protons, some of them are neutrons. And then we'll just draw the first two energy levels and do an arbitrary number of electrons. In this case, I'm doing 6. So this is our nucleus, which is made of protons plus neutrons. These are discrete energy shells. And then we've got our electrons. Now, at GCSE, they teach you the relative charges. So what you would be familiar with is protons having a charge of +1, electrons having a charge of -1, and neutrons having a charge of 0. From now on, you're going to learn the charges measured in coulombs. So in physics, we're not doing +1s and -1s anymore. You're going to learn the actual charges, and you're going to memorize them. So the electron charge is minus 1.6 times 10 to the minus 19 coulombs. And the proton charge is the same but positive, plus 1.6 times 10 to the minus 19 coulombs. Put a box around that because you need to memorize that. The neutrons are neutral, which means 0 charge. And our protons and neutrons will be referred to as nucleons. And we call them nucleons because they live in a nucleus. Now, atoms are neutral because they have equal number of protons and electrons, which means that their charges will cancel each other out. So overall, they have a charge of 0. The moment that you either give them an extra electron or you take one of their electrons away, we stop calling them atoms and we start to call them ions. So if they gain or lose one or more electrons, we call it an ion. Next we'll do a subheading, nuclear shorthand. So the nuclear shorthand is just how we write about different atoms as their symbols and numbers. So I'm going to start with an arbitrary atom or element. We're going to call it X. And it has two numbers, the A and the Z number. A being the top number, Z being the bottom number. The top number A, we call it the nucleon number in physics. So that's called the nucleon number. It's called the nucleon number because it's how many nucleons it has. So it's simple. In chemistry, you might have called it previously the mass number. But we don't call it the mass number because we associate mass with the units of kilograms. Whereas if we think of helium, which is 4.2, helium does not have a mass of 4 kilograms. Yes? So it's called the nucleon number. It has 4 nucleons. We keep it simple. The Z number is called the proton number. And in chemistry, you might have previously called this the atomic number. Why do we call it the proton number? Because how many protons it has. So, for example, if we've got lithium, which is 7,3, this has 3 protons, 3 electrons, 7 nucleons, which means it has 4 neutrons. Next, we'll do a reminder of isotopes. Again, this was something that came up in GCSEs. So let's get the subheading isotopes written. So isotopes are defined as same number of protons, different number of neutrons. The proton number has to be the same because to be an isotope, you must not change the element. So an isotope of hydrogen must still be hydrogen. If I change the proton number, the isotope is no longer a hydrogen anymore. It'll become something else. So isotopes are same number of protons, different number of neutrons. So, for example, if we look at hydrogen, it's H11. Has 1 proton, only 1 nucleon, which is that proton, and 0 neutrons. You can have isotopes of hydrogen, H21, for example. While this is still hydrogen, because it's one of the common isotopes that we deal with, we've given it a unique name. We call it deuterium. Not every isotope of every element will have its own unique names. But deuterium is still hydrogen. It's just a heavier form of hydrogen because it has one proton plus it's got a neutron. And then you can have another one called tritium. Again, it's still hydrogen because it's only got the one proton but different number of neutrons. Next, I'm going to give you the masses of the subatomic particles. And again, these are numbers you have to memorize. So, at GCSE, you would have learnt them as relative masses, where you would have said the proton and the neutron were 1. And you would have said the electron was 1 over 2,000 or 1 over 1,850. But now you have to learn them in kilograms and memorize these numbers. So masses. So mass of the proton is equal to 1.67 times 10 to the minus 27 kilograms. The mass of the neutron is almost the same, but it's slightly heavier. Now, doing it to 2 decimal places, you won't see that the neutron is slightly heavier. Okay? So for most calculations, we're using the same number. Where you have to use the heavier calculation, the question will refer to the data sheet or will give you the data in a different form. But that's quite rare, and the question will make that obvious to you. And then the mass of the electron is equal to 9.11 times 10 to the minus 31 kilograms. So these are all new values you need to calculate, remember, memorize. Let's start a new page. The title here will be specific charge. Now first I want to go back to GCSEs a little bit and explore this word called specific, because it has a meaning in physics. So the word specific in physics means per unit mass. It means divide by mass. When we have the word density in physics, it means per unit volume. So normally what we refer to as just density is actually the mass density of an object, where we take the mass and we divide it by its volume. So we're looking at how concentrated within a volume is that mass. Now I could have a charge density. So if you imagine 2 spheres that have an identical charge on them, but one sphere is bigger than the other, the charge density will be greater on the smaller sphere because the charges are more closely packed together. Now, that works well for large objects, but if I start talking about subatomic particles, we talk about protons, electrons. Well, what is the mass? Well, we know the mass. What is the volume of a proton? What's the volume of an electron? The bigger question is, do they even have a volume? Are they actually tiny little balls of matter that we imagine them to be? Or are they more complex? So we know what their masses are. We don't know if they have a volume. They probably don't have a volume because they don't always behave like particles. They sometimes behave like waves. So instead of finding its charge density, we find something else called the specific charge, which is the charge to mass ratio. So this is the charge to mass ratio So the specific charge is Q over M, where Q is equal to charge measured in coulombs. M is the mass measured in kilograms. And so if we did this for a few examples, so for electron, Q over M is equal to minus 1.6 times 10 to the minus 19 divided by its mass, 9.11 times 10 to the minus 31. And that should give us roughly about 1.8 times 10 to the 11. And the units are coulombs per kilogram. So it's C kg to the minus 1. For a proton, we do charge over mass times 10 to the minus 19 divided by its mass, 1.67 times 10 to the minus 27. About 9 point something. Someone calculates it. Is it 9.6 times 10 to the 7 coulombs per kilogram? So looking at this, the electron has the largest specific charge. The proton, while it has the same charge, because it's more massive, it's got a smaller specific charge. Now, if we go any bigger than that, we're going to have helium. Helium now starts to have charges in its nucleus, so the protons, but it also has the neutrons. And the neutrons increases the masses without increasing the charges. So the specific charge, as you go to larger and larger atoms, will decrease. But a point here is, I'm not talking about specific charge of the whole atom, I'm talking about specific charge of their nucleus. Because the whole atom doesn't have a specific charge, because it has no charge. So the only things that can have charge is the subatomic particles individually, or the nuclei of atoms, or ions. So things that have charge. Neutrons don't have a specific charge. They don't have charge. Atoms as a whole don't have a specific charge because they don't have a charge. Okay? Next. Yes?
In exam, we don't specify like 2 decimal places or 3 decimal places. What's the most common?
Okay, that's a good question. So in the exam, they won't specify to what decimal places. What do we do? So we don't talk about decimal places first. We talk about significant figures. Okay? Then you match the lowest significant figure that was given in the question. So if the lowest significant figure in the question was 3 significant figures, you give your answer to 3 significant figures.